Awesome. We are recording. So again, just a few housekeeping items. We do ask that you kind of minimize your camera use. We are expecting a large crowd today, and sometimes that helps. As Barbara is speaking, Dr. Dahl, please feel free to use the chat to ask questions, and we will address those at the end with our moderator. And we do have several requirements for those PDH credits that I just mentioned. So please read through your email thoroughly. If you did not receive the information, I'm happy to resend that or share that with you. I know sometimes that can end up in spam. It's going to several different people and it has an attachment, but we do have 3 different requirements. There will be an online survey that opens up and then a sponsor evaluation that we ask that you fill out. So if you have any questions, feel free to reach out to me about that. And yeah, the one thing I do want to mention quickly is NCWRA is going to join WRI at our annual conference coming up March 23rd and 24th. That will be held here in Raleigh this year at the McKimmon Center, and it is a hybrid event. We have plenty of in-person space left, lots of room to spread out and socially distance ourselves, but also to get back and see your comrades. We've been missing that in-person interaction lately. I know I have. So please check out our website. And I think we're going to drop a link here in the chat. If you haven't already seen that, there is a draft agenda available. So lots of good topics coming up. And yeah, we have sponsorship and exhibitor space available. So again, that's March 23rd and 24th. If you can join us, we'd love to have you. So with that, I'm going to go ahead and turn it over to Matthew Hornak. He is NCWRA president, and he will officially introduce our webinar and our speaker for this morning and get us rolling. So Matt, you may take it away.
All right, thanks, Anna. Yeah, as Anna said, you know, we're NCWRA, and my name is Matt Hornak. I'm the president right now. So we will be at the WRI conference, as she said, so we'll have a booth there. Please come and connect with us. We'd love to connect with you. And if you want to save some money on your registration, you can join NCWRA, and that'll save you some money. So I think that's a great thing to look out for as you're registering. As president, I want to thank everybody for your attendance today. I know that this webinar is going to have a lot to offer you, but your attendance also helps further the NCWRA's objective to promote water resources research and development and management in North Carolina. And so with that, one company that is helping to further that objective is today's sponsor for this forum. So Resource Environmental Solutions, otherwise known as RES. Let me see if I can get to their slide. So RES, they're a national operating company that's focused on restoring a resilient earth for a modern world, project by project. And so they are the nation's largest ecological restoration company, and they support the public and private sector with solutions for environmental mitigation, stormwater and water quality, and climate and flooding resilience. And they have a unique operating model for delivering ecological uplift. It's based on science-led design and full delivery and long-term stewardship and guaranteed performance. And so they design, build, and sustain sites that preserve the environmental balance, lifting impaired ecosystems into restored health and ultimately self-sufficiency. And so we're very thankful for RES and their sponsorship and for supporting our association. And I'm sure everybody on this should be on a computer right now, so please check out their website. It's at the bottom of this slide, but it's res.us. So go ahead and look at that and browse that while we get started here. I do want to switch and introduce our speaker today, and probably most of y'all know Dr. Barbara Dahl, but for those who haven't had the pleasure of meeting her, let me introduce her to you. Dr. Barbara Dahl is an Extension Associate Professor in the Bio and Ag Engineering Department and an Extension Specialist for NCC grant based at NC State University. And so Barbara holds a Ph.D. in Bio and Ag Engineering, and she's also a licensed professional engineer. And Barbara leads the Stream Restoration Program at NC State University, which carries out research and trains students and conducts numerous training workshops for professionals and organizes EcoStream, the Southeast Regional Stream Restoration Conference. Barbara is currently the principal investigator for more than $1 million in grant funds and leads a team of engineers and students that conduct outreach and research projects focused on evaluating the performance of stream restoration efforts, developing new techniques for ecological restoration, and assisting communities with flooding and water quality challenges. So, as y'all know, she's very well qualified to be presenting, and we're really excited about hearing about natural infrastructure for flood mitigation. So Barbara, I will stop sharing my screen and let you take over. Thanks, Barbara.
Well, thanks for having me here. You'll see yourself for a second there until I get my slides up. All right, everyone see my slides? Let me move that over. Good. All right, well, thanks for having me here today. I'm really excited to be presenting this work. We've spent several years kind of working with communities on flooding and delving into this kind of integration of natural systems with flood mitigation. Before I start, I want to acknowledge my kind of co-authors on this work, Dan Line and Dr. Jack Kirky-Fox. They do all the really heavy lifting on the modeling work that I'm going to be sharing with you. I'm just the idea person, and they have to make it all happen. And at the bottom here, I have a lot of logos for different partners. We have been collaborating with a lot of groups to dig into this dealing with flooding and natural infrastructure. And so I want to recognize that this work I'm presenting also has a lot of input and funding support from different groups. So nature-based solutions, as it's sometimes called, is where we would use natural systems to try to store water temporarily to mitigate flooding. And here in the Bio and Ag Engineering Department and with North Carolina Sea Grant, we've had a long history with stream and wetland restoration, as well as at NC State. We partner a lot with the Forestry Department, and they've done a lot of work. And we've also looked at water management in agricultural settings. So we wanted to really take a deep dive at these practices and see how can we use those to mitigate flooding. And so that's a real big question. The approach that my group has taken is that we first work to identify opportunities. Say, where can we put this stuff out on the landscape? Then we do a lot of modeling, hydrology, and to look at what kind of flow reductions we could achieve. We also look at river hydraulic models to say what change would that mean to the water surface elevations as water is flowing down the river system. So kind of going from the watershed into the river system. We've also done some work to model water quality benefits of these practices and some cost estimates to look at the cost of implementation as well as the benefits of this. So I'm going to kind of talk about a lot of the work that we've done. One of the first projects that we did to look at natural infrastructure was looking at 2 creeks in Goldsboro with a small project that was funded by the Environmental Defense Fund. I'm going to just kind of recap the major findings of this before I move into our kind of bigger study. We looked at Stony Creek, which is about 31 square miles, and Big Ditch was only about 3 square miles. We looked at kind of 2 different types of natural infrastructure approaches. Big Ditch is a very urban watershed in Goldsboro. It's small, but it has about 93% developed, a lot of impervious cover. This channel is very modified. It has been straightened, armored with concrete, and it has a lot of crossings on this. In fact, there's 22 crossings on the stream, and many of them are undersized. We saw that 16 of these crossings are overtopped in as little as the 10-year storm. So the flooding of roadways and as well as homes and structures in the corridor is a real problem in this watershed. So what we wanted to do is kind of take a look at different approaches. The kind of more strict civil engineering approach might look at just the culverts and the bridges and how could we address those. And then the ecological restoration person might just look at the stream channel and say, well, we'll just do a restoration and expand the floodplain. So we wanted to look at these things individually and in concert. So we looked at the crossings and we identified that 7 of these crossings shown in gray here are really critical to transportation. And so we looked at enlarging those crossings to provide capacity in much larger storm events. Then we saw that on every small street, every block crossing the stream, there were these other very undersized pipes. And we're like, we could remove these and the transportation would still be very easy because they only have to go a couple blocks away to be able to drive over the creek, and then use this area to then widen out the creek instead of having this very channelized ditch to have more of a stream channel with a floodplain. So we looked at a floodplain that was 6 times wider than that channel. So this would allow for a more naturalized stream with a lot more flood capacity to it. And to cut to the short of this, when we looked at individual practices of just addressing the road crossings or just doing the stream restoration project, we had very little effect on the flood profiles, the water surface profiles when we looked at the hydraulic model. But when we did those things in combination, we saw great benefit all the way up even to the 500-year storm. This blue line is from the existing water surface on Big Ditch in the 500-year storm. So when you see these water levels jump up, that's where there's this really undersized culvert pipe. But when we did both the floodplain expansion and removing the redundant road crossings and enlarging those 7 critical crossings, we saw a dramatic reduction in the water surface elevation, again, in both the 100 and the 500-year as well. And if we when we looked at the inundation or kind of the footprint of that flooding, we saw a great reduction in the flood footprint as well. So that would mean a lot of structures that were getting flooding would have less flooding or no flooding on them, and other areas would have lower water levels. So the red is where the new water surface inundation would be, kind of more confined to where you create that new floodway. Well, this would require buyout and relocation of structures, as well as, again, we have to do the bridges as well. So the flood mitigation has to be comprehensive or multi-pronged. It cannot just be buyout. It cannot just be addressing the roads crossings or doing the ecological restoration. We have to do all of these components together to achieve flood mitigation and resiliency in this location. Well, the second creek, Stony Creek, was a whole different kind of setting for this flooding situation. With Stony Creek, which is a much larger watershed, the upper half of this watershed is predominantly agricultural areas. And then that water then flows through the different branches of Stony Creek down into Goldsboro, where the flooding is a real issue, including a roadway that leads to the hospital often is flooded on Stony Creek. And so we looked at the concepts of storing water in that upper part of the watershed. So instead of giving more floodway, how can we have temporary detention of water in storage areas, or to reduce runoff through reforestation? So we looked at those two things individually and combined. So with our storage and retention, we found these areas which are hatched out here in blue out on the extremities of the watershed, where we could put in low berms of about 2 foot with a control structure that would be a managed system to hold water temporarily when it rains. So these structures, these berms and structures, would not hold water on small storms. They would be only operational for larger events, 25-year storms and above. And again, we looked at low berms, only a couple feet. And then we looked at a theoretical reforestation of all ag areas in the watershed to see how much reduction in flow we would achieve from that. So we had about 30% of the watershed that we reforested. And then we looked at those things in combination. So the storage retention areas comprised only about 10% of the watershed. And so when we looked at the various peak flows for our return interval storms, in the blue you see we have the existing condition. And then we have with just storage retention, then reforestation, and then the combined. And you can see with the combined, even up to the 500-year storm, we had about a 28% reduction in the peak flow. Now, we were affecting a large portion of that watershed with that reforestation, which reduces the amount of runoff, and with that 10% of storage area. So we saw some substantial reductions that were quite encouraging for us. Well, this led to a larger project that we completed last year for the NC Policy Collaboratory that we did with a number of partners. And we used that similar approach of identifying opportunity, modeling, and then looking at cost. In this case for this went much further. So how we did this project, we looked at the full middle Neuse Basin. So we were not focused above Falls Lake here because all the runoff is already, you get flood mitigation with the Falls Lake Dam and water control structures that are there. And so our study did limit to the extent of Kinston. And we picked 3 study watersheds within the Middle Neuse to focus on. These are watersheds that have a USGS gauging station at the downstream end that we could use for calibrating our models and validating the models as well. And they're fairly small, so we feel like we could take a very deep dive at that identifying opportunity and the modeling on these, and then use what we learned from these watersheds to extrapolate back out to all these other subbasins in the Middle Neuse and see what kind of reductions would we then achieve on the Neuse River itself. So we identified potential sites. Well, what we did is a GIS process that you've probably seen a lot of other people do, where they use soils, land use, topography, all these various variables, and kind of overlay those and say, oh, voila, here's where we can build wetlands. Here's where we could maybe do some water farming. And so then we took that a step further than kind of that typical just overlaying these GIS layers. And we went to the field and we ground truth 241 locations in our 3 study watersheds. So you can see here's Nahunta and Bear where we looked at those sites. And what we saw is when we got to it is many sites weren't really a good fit for the practice that we had identified through our GIS process. So we did a lot of refinement work based on that field work, plus also starting to look at aerial photos and other information as well. And so when we refined our GIS, we realized we needed to limit the slopes that we looked at for certain practices to be about 1%. We were going to have to buffer around roads by about 20 feet. We had to put 100-foot buffers on structures and waste lagoons and remove very small parcels of 4 acres. So our initial process was turning up these areas with too steep of slopes that, would show water farming around, all the way around and circling a different structure, or very small parcels. So with that kind of resolved a lot of this inappropriate sites for what we're looking at. This is Nahunta Basin. And in yellow, it shows the initial sites that resulted from that, just kind of overlaying GIS layers. Whereas once we refined and really got to the nuts and bolts of what would be practicable, these red sites are where the actual opportunity that we felt was more reasonable did exist in this basin. So with water farming, I've brought this term up, and I want to just talk a bit more about that. Basically, this is an engineered system that's designed to retain water and slowly release it in order to actually have some water quality benefit, because it allows time for nutrient processing, but can be used to reduce flooding. This practice has been done in Florida. This is the Calkins farm there. And in Florida, they have done it predominantly for a water quality benefit to reduce some of that nutrients that are leaving some of this farmland. It does require a berm or terrace along the edge, and you have to put control structures at all the outlet points or where ditches are leaving from that farmland. And this would be equipped with some type of structure such as a riser or weir. Now, we found the most appropriate locations for this where it's agriculture that's not already in the floodplain. So if it's getting flooded in the 100 or 500 year storm, we don't need to try to store water there. A slope of less than 1.1% ended up being our focus. And we looked at contiguous areas of at least 20 acres. So you had something substantial and not just piecemeal areas of land for storing water. Again, these sites are not set up to hold water at every storm. They would be managed. They're not passive, where there would be a close off of the outlet structure that would be installed prior to the larger storm event. And then after a few days, the gate would be open, that structure would be open to let that water back out. So you're holding water for a short time period to release it after peak flows have pass through the downstream areas of concern. And what we did with our sites is we actually picked out about a dozen sites where we said, what would the water farming system look like? What would it have to consist of in these areas that we've identified? So using the digital elevation model data and the hydrography data, we identified where berms would be, which are shown in red. Here's a couple of our sites. We also looked at where the outlet structures would have to be. And this enabled us to then also be able to calculate how much volume of water would be stored. What's the footprint that would be impacted by this water storage area? And we could also look at costs, because we looked at what height would these berms need to be and how many structures and what the costs. So this kind of case study designing of the water farms really helped us look at a lot of different things we needed for our study effort. We got down into kind of the nitty-gritty of water farming. So this shows you some of the sites identified for Bear Creek watershed, the yellow hatched areas. In Nahunta Farm, you can see the sites we had here. And this shows you then we extrapolated that process to the middle Neuse of what we learned to show what kind of opportunity was in our full study region. And you can see in the lower part of the basin, this is where we had the greatest opportunity as much. In fact, our study basins were two of the highest. We have another pretty high here, and just limited opportunity in the upper part of that middle Neuse Basin, again, really because of the slope, that 1.1% cutoff, and that we had to have open land that was being farmed in order to do that. So we only had about 1.1% opportunity in the full middle Neuse. We also looked at flood storage wetlands. Now, wetland restoration in the eastern part of the state has really been dominated where they plug ditches, they create microtopography, plant vegetation like this. This is not what we are considering for this, because these areas would be already full of water by the time you're at a 100-year storm, or they would fill very quickly. They don't have a storage component. We need a storage component to be able to mitigate flooding of a 100 or 500-year flood. So we wanted to construct drainage features on ditches or small streams and install, it would have to have maybe some excavation to bowl out an area, build an embankment, and have a structure that would slowly release the water during storm events. So this is a graphic the College of Design created. This is more the concept of a linear wetland that could be created on a agricultural ditch. Again, this area would have minimal amount of water, less than a foot. It would operate as a wetland at any given time, but there would be this embankment with an outlet pipe that is what we modeled for our purposes that would retard that water, retain it, and release it more slowly. And so we'd get that mitigation, and we optimize sizing of this structure to provide mitigation in the 100 and 500-year storm events. So then we set about, in fact, with the way we size this, we looked at being able to achieve about 80% peak flow reduction in the 100-year storm and 40% reduction in peak flow for the 500-year storm event. But how we had to do that is locate using the digital elevation models and the hydrology data sets to see where we had small ditches and creeks that drained at least 35 acres. So it wouldn't matter if you had a lot of storage if you don't have a watershed that's contributing to that area, right? You might have a bowled out area, but if it only has a 1 acre watershed where you're not getting much storage. So we needed those ditches that had some watershed area draining to it, or small channels. And so this is the process that we did for that. And then we identified where the wetland would be on each of these channels. So where that bowled out area would need to be created to provide that storage, and the earthwork needed to be able to create that berm. And so again, these wetlands, in order to get that 80% reduction in the 100-year storm flow peak, these wetlands we optimized at 10% of the size of that drainage area. So each wetland would need to be 10% as large as its contributing watershed area. So here on Bear Creek, you can see in red, these are all the wetlands that we identified, and the blue hatched area is the drainage area for that wetland. So again, these wetlands are about 10% the size of that drainage area. Here you can see similarly for Nahunta Swamp, the areas that were identified. So then again, what we learned with that procedure, that really refining our GIS process and using those digital elevation model data, we extrapolated that to the other subbasins in the Neuse. And you can see the opportunities are really isolated again, more to the lower basin, where we have those open areas without roads or buildings, and we could identify those kind of available channels, and very little opportunity, or much less, in the upper part of the basin, again, because of those steeper slopes, more development, and less open land in these areas. So we ended up very high levels in Bear Creek, good levels in Nahunta, about 5.7% of the watershed. This is the wetland drainage area. So this is the proportion of land that would be controlled by the wetland, not the footprint of the wetland itself. Then the last practice we looked at was reforestation. So we focused in on low productivity cropland for this. We used the National Commodity Crop Productivity Index and looked at where we had lower scores to identify potential areas where that lower productivity land could be converted to forest. So in Bear Creek, you can see we had a lot of opportunity identified down towards the lower portion of Bear Creek itself, not much in the outer portion of that watershed, and not as much opportunity in Nahunta. Most of the cropland was very productive there, so that would not be an area we want to take out of production to convert it to trees and forest. Little River, we had a modest amount of opportunity there. That looked pretty good. And then extrapolating out, unlike the wetlands and water farming, we see a greater distribution of this opportunity within the middle Neuse Basin. So Little River had about 6.5% a good opportunity, remember, in Bear, not much in Nahunta, and about 8.4% for the middle Neuse Basin. So then we built very detailed models for Bear Creek, Nahunta Swamp, and Little River. We modeled those in existing condition, and then we went in and modified those models to incorporate the storage components, the changes in runoff from reforestation, to simulate that natural infrastructure throughout those 3 study watersheds. And so looking now, we're getting to some results finally, now that I've kind of laid out everything that was done. Well, if we look at the peak flow from Matthew and Nahunta Swamp, here's our totals of opportunity for the 3 practices in Nahunta. And what we can see here is the existing condition flow during that Hurricane Matthew. We can see with reforestation only about a 0.6% reduction, because remember, it had low opportunity for that. 7.7 for water farming, 8.9% for wetland, so pretty good reductions. And that combined approach of water farming and wetland gave us 13.6%. So no combined with reforestation was in there, because the other practices kind of overlaid those areas. This would result in about a 0.4 foot reduction in the water surface of Bear Creek at the mouth, at the lower portion during that. So that's not a whole lot of elevation change in the river. And so we can look at that. Here's the 100-year storm, which is kind of pretty comparable to Matthew. If we look at a cross section of the river, this is that inundation footprint in a 100-year storm. You can see here's the channel here. And when we're at the point of the 100-year storm or Matthew or these very large events, we're well out of there. So that amount of flow, that reduction would only result in that 0.4 feet of lowering the water surface for that. If we look at Bear Creek, we can see these are the opportunity amounts. Again, a lot of wetland opportunity, a lot of reforestation, pretty good amounts of water farming, and we can track those changes of the individual practices. Going very high. In fact, when we reach these different combination approaches, in fact, all three of water farming, wetland, and reforestation having over 20% reduction in peak flow. This would equate, in contrast, to about a 1 foot drop in the water surface elevation at the mouth of the creek during this was Hurricane Floyd, was our calibration validation storm for Bear Creek. With Bear Creek, with the 100-year storm, if we look at the cross section here, what we can see is, again, this is our channel, this is our floodplain area. When you're in a 100-year storm, we're way out onto the floodplain. And so that, even though it's over 20% reduction, you're kind of bringing that flow down lower in the floodplain. The footprint of that flooding is not going to change substantially. You can see that fringes of areas that are not flooded with this. So the blue is the with natural infrastructure, and this white hatch is without it, the existing condition. Again, that's 0.8 feet for the 100, and it was about 1 foot for Hurricane Matthew reduction. What we saw is there was a real distribution. We looked very closely at Bear and Nahunta, and we saw very high variability in this peak flow reductions in the watershed, some low, some much greater, depending on how much the kind of density of natural infrastructure immediately above that area. And we did a lot of looking at variation of that with our process. And so you can see some areas with very high reductions in the peak flow with that. So some of these areas very high reduction depending on its location in the watershed and the synchronization of, or asynchronization of the flows, desynchronization of flows. So then we took everything we learned from those three basins and we extrapolated again to the full Middle Neuse to model peak flows. So I say that all in a few words, but this was a pretty complex process that I'm not going to have time to review in detail. But once we did that, kind of modifying the overall Neuse model, we used a model of the Neuse that was developed by AECOM for North Carolina Emergency Management, and we went in and made changes to simulate the other basins, as well as everything we learned in detail from our 3 study watersheds, and looked at the peak flow reductions of those. And you see the lower part of the basin having some very substantial peak flow reductions in areas, 18, 20%, above 10%, and very little in the upper basin, because again, most of our opportunity was concentrated to the lower portion of the basin. And so here's the overall Middle Neuse opportunities. You can see reforestation being the dominant opportunity throughout the basin. We also used the existing hydraulic model for the Neuse River, and we looked at the peak flows as well. So what the consequence of the peak flow reductions would be to the river. So if we look at the peak discharge reductions, we focused on the 3 communities down the Neuse, Smithfield, Goldsboro, and Kenston, and with our various practices of reforestation and the combined practices of water farming, wetland, and then all 3. And we could see at Smithfield, we really had no reduction. That's just because there was so minimal amounts of opportunity above there. Whereas in Goldsboro, we saw with that combined approach up to about 4.4% reduction for Hurricane Matthew in peak discharge, and about 5.3%, just slightly more, at Kinston. And we can see that this resulted in about 0.3 feet reduction in the water surface at Goldsboro and 0.4 feet at Kinston. So just like Nahunta and Bear Creek, what we see is that when we're in these large events like the 100-year storm or a hurricane event, the channel is here, the river. In fact, at Kinston, the river has kind of two prongs. It has the main part of the river and it has a kind of flood overflow channel that's not as deep. But in these storms, we're way out onto the floodplain. This is the 100-year storm. So even if we lowered the water by 1 foot, we'd still not change the kind of footprint of flooding. We're going to mostly be bringing that water down. So I guess my message here is to point out that that's the natural process. So we have a channel, we have a floodplain, water's going to be out. When we're at a 25-year storm or above, water's going to be out onto the floodplain. So it's still very important that we get these structures out of the floodplain, that we're not going to kind of mitigate our way out of flooding the floodplain. So even though the water surface reductions were pretty small, we did see some significant damage reductions. We looked at the 25, 50, 100, and 500-year storm in Kinston and Goldsboro. We did not look at Smithfield because, again, the reductions in water surface were not there. And we saw anywhere from 7% reduction to up to 21%. We use the NC Feynman data that gives you every half foot of what structures are inundated and the cost of that. And so the cost reductions would be greatest for around the 50-year storm. We did water quality modeling as well. We looked in very close detail at the reforestation and wetlands in Nahunta Swamp and Bear Creek. We used a SWOT model. In Bear Creek, for example, we found over 15% reduction in TN and TP, total nitrogen and total phosphorus, with the wetlands and reforestation. Notably, in Little River, we only affected about 6% of that watershed with reforestation. We had 12% and 17% reduction in TN and TP for that watershed. So that was a very good reduction we saw for that. Here's some of the, with reforestation, wetland, and the combination of the two in these watersheds. We also looked at sediment load reductions and found very great reduction. You see on Bear Creek about over 30%, 16% for Nahunta with that combined approach. We looked at what the nitrogen credit would be for that. I'm going to just show you the combined where it's wetlands and reforestation using the 2020 values of per pound for the Neuse River. And what we found is that about $2 million annual value and almost 59 million for the 30-year credit. And in fact, this would cover about 23% of the cost of the wetland restoration work. So that was very encouraging. We did other economic analyses working with multiple partners. UNC Chapel Hill and the Soil and Water Conservation Foundation they conducted workshops with farmers. They did surveys with them and came up with what were the optimal leasing and or purchase options that would be potentially acceptable for farmers to do water farming. I showed you some of the direct cost work we did of actually looking at theoretical designs of wetlands and streams. We worked with the forestry department and we came up with what the actual cost would be to implement all these practices in the Neuse, Middle Neuse. We looked at what type of investment returns and upfront cost incentives would be needed for landowners. The forestry department at NC State did that. We looked at spending pathways for restoration work based on past funded work that's been done by providers for the Division of Mitigation Services and other projects, working with some of the mitigation providers. We also did as I already showed you, the structural damage reductions down the river. We looked at the water quality benefits, which I showed you those nitrogen credits. And then UNC Chapel Hill looked at kind of direct economic and then economic multipliers of doing this work. In other words, if you put the work out there, you're not just, if you spend $1 on restoration work or water farming work, what does that mean to the local economy and jobs? I just want to kind of give a couple quick slides to show the results of that. And so we found that the acres that we affected would be about over 112,000 acres. This was about 10.5% of the basin. The cost to implement everything would be about $726 million. That's a lot. A lot of that is in the wetlands because of the amount of earthwork to do those. However, and the cost per acre is very high. However, we can look at the water storage potential for the wetlands is 3 to 6 times more than the other two practices. But if we look at just the construction of these, not considering maintenance, we see that the direct jobs that would be created would be around 1,600 jobs. Then we get those indirect jobs created in other industries for each job, each project that you would do out there. That would be almost 9,000 jobs of the kind of multiplier effect. And for every dollar that is spent there, you would have $1 return in the local economy. So that 726 million translated to about 791 million benefit to the local economy. And we found that the indirect or that spillover effect was over double for these different practices, higher for the wetland restoration because of all the kind of more detailed construction work that goes along with that. So just going back, that putting that dollar out there doesn't mean you've just thrown it away. It's absorbed into the local economy. I just have a few quick slides before I wrap up, showing you the Grand Forks, North Dakota, and some other areas around the country and the world doing this nature-based solution type work. Grand Forks, I picked this because it's a fairly small city of about 57,000. As you know, most of our communities, especially in eastern North Carolina, are very small. They're grappling with tremendous amounts of flooding. So they, in Grand Forks, had a very bad flood in '97. They also had a fire at the same time. So it was a pretty tough time for them. And what they did is they came up with a master plan for a greenway that included a lot of elements. They bought out 50 homes that were repetitive loss structures. They built flexible flood walls and levee system in areas that they were not able to move. That was part of their kind of downtown. They could not relocate. They implemented this 2,200 acre park and a 20-mile greenway system, trails through this area. And this really, they didn't just build it, they actually programmed this out. They had lots of activities in this greenway and floodplain corridor. So we can see here's their flexible flood wall. Their berming, some of the berming that had to go in with this, and you see all this greenway activity. This is pretty soon after construction. And lots of activities that go on. Even cross-country skiing takes place in events in this area, and it's actually revitalized their economy in this community. So I guess the point here is to show this is not devastating. I've shown you a lot about storing water in the watershed, but actually recovering floodplains for storage of floodwater can have benefits to these communities. It's not always a loss. This is something in the Netherlands. They're masters of water management, but they're also realizing they've done very engineered systems, and they're trying to do more ecological or nature-based approaches, as they like to call it. And so they're looking at moving things away from the river in order to recover more floodway for their streams and rivers, getting out of some of the more managed systems and providing that area for their streams and rivers. So this is the room for the river approach, where they're moving this levee further out. It was over here closer to, further away from the river. So some final things and conclusions to consider. We have a lot of communities, and especially in Eastern North Carolina, they're very small. They're going to need a lot of financial and technical assistance all the way through all phases of different flood mitigation projects. Innovative multi-pronged approaches are going to be necessary. If we have just the kind of ecological restoration people doing their work, and we have maybe DOT and the civil, just straight civil engineers doing their work, and we have Cornell doing buyout, and we don't integrate these things, we're not going to optimize our opportunities. We have to do this kind of optimization and integrate a multi-pronged approach. We've got to better communicate the risk and uncertainty of future flooding. I showed you the floodplain is going to continue to flood, and with climate change and warming, we're seeing that's likely to happen more frequently. We've already experienced that in the last 20 plus years. We've got to relocate structures out of the floodplain. Again, the floodplain will continue to flood. We will not stop that with natural infrastructure or any other measures. We've got to identify safe places for people and a place for the water, because what I've seen is water generally always wins. And the most important use of floodplains is to store flood waters. We have to remember that. Recovery of these floodplains can create beneficial opportunities. That's a type of nature-based solution in and of itself. So we have this website that details a lot of our kind of work we've been compiling in this topical area of flood mitigation and natural infrastructure. So feel free to go to that. We have some full reports on the work that I have shared with you today. And with that, I'll stop sharing. I hope I haven't talked you to death, and we're open to take questions.
Yeah, Barbara, that's great. Let me start my video back up. I'll go ahead and put our slide up just so we can have this up while we do questions.
I see some in the chat. If you want me to tackle them first.
Yeah, there are a couple in there. If you want to, I saw Francine and Scott had asked some questions. So if you want to tackle those, that would be great.
So would it be necessary to obtain an MPDS permit for flow of the water farm? I'm not sure, Francine. I think it would have to do a little bit with the maybe size and designation of that kind of creek. I talked about identifying those creeks or ditches that drain at least 35 acres. I think some of those may be blue line streams that, yes, would require a permit. Others may fall outside of that. So that would be, we have the SWITC training course here too, that kind of how DEQ goes out and categorizes a stream as whether it falls into the buffer or the 40441 rules. And so that would come into place here. So it may on some and may not on others. Scott, would there be even further benefits for the smaller, more frequent events? Again, I showed, the damage reductions were greatest for the 50-year storm. And so with Stony Creek, I do believe we looked at some of the smaller events and saw benefit. However, the approach we used is for this particular project and the work we've done is we've looked at damages across Feynman, and where you really start to hit major damage, surprise, surprise, is getting close to the 100-year storm in most places, not all. Some of them start seeing serious damages at 50. Well, that's because we've kind of tried to restrict or keep development out of the 100-year floodplain. So everything we did was really with those larger, we were really looking to the 100 and 500-year storm. So everything we were maximizing the kind of flood benefit for that. And so that's why a lot of ours really does have the greater benefits at those. Now, if you were wanting to deal with smaller storms and more flash flood events, different, localized flooding, then you might have a little different approach. We did a DOT study where we looked at 8 tributaries that have flash flooding in those 3 Neuse communities. And we focused in more on the culverts and bridges that were undersized. And we were able to really have great reductions with addressing undersized infrastructure. So that's kind of my point. In some cases, it may be more that infrastructure, it may be natural infrastructure, gray versus green, but you might have to do that combination, and you have to kind of set that criteria for what is it that you're really trying to achieve. All right, we have what other larger watersheds have been looked at, particularly interested in the Northeast Cape Fear. We have not done any modeling on that. Again, our work, we have done the Kashai River in Windsor. We've done some work, and we've done everything else has been focused in the Neuse with the kind of projects and funding we've had to date. And we kind of built on the Neuse because we've learned a lot about that, you know, area and those streams through our DOT work and the EDF work, and then with this collaboratory. But I think this could be done in other watersheds to look at that opportunity.
Yeah, Barbara, I know you mentioned AECOM did this Neuse Basin study initially, looking at the overall basin, and emergency management through some of their contractors has also done the Tar River Basin, and they're working on the Northeast Cape Fear River right now. So that's something emergency management will probably release, and then maybe Barbara can look at that and take some of that data and do the same type of stuff, which would be awesome. That's all the questions we have written right now. Here we go. Tim Orman asks, could you describe the flood damage economic modeling in more detail?
Okay, so the flood damage, what we did is we only looked at individual storms, and we used the peak flow reductions, plugged those into the existing Neuse hydraulic model, and we got those water surface reductions. So we looked at Kinston and Goldsboro, you know, where they have detailed information on with the NC Feynman tool again. So you can change the water level every half a foot, and it'll tell you how many structures are inundated and the cost of those damages. So in other words, when we had that point, we had to do some interpolation between that, because remember I showed about 0.4 foot reduction, 0.5, I think, or 0.3 and 0.4 for certain storms for Goldsboro and Kinston. In addition, we did that, extrapolated some of that to areas outside of the kind of what they call Feynman libraries. In other words, they've taken the digital elevation models around that Feynman area, and they've got real good detail about where water goes and how deep the water is, and they've got finished floor elevations. So we looked at the overall value of structures and some of the other reaches, you know, near there where we were seeing some lowering of the water, and we use those kind of reduction estimates to kind of say how much more that would be. But we did not do the full benefit cost approach that is the FEMA approach. We don't have that software or that training. So we were doing something more isolated to what we could do with the resources we have. We did not look at secondary impacts. You know, we were looking only at the structures themselves, so the damage reductions are really small compared to that $726 million price tag. But again, a full FEMA one would look at a 30-year type scenario, what frequency of storms, and they would look at secondary impacts. We did look at a theoretical 30-year based on what has happened over the last 30 years. So that, and then we looked at another scenario where we said, well, what if we got a 500-year event, which we haven't had? So again, but we didn't, it's not following that FEMA guidance at all.
I didn't want to miss, Marshall Taylor had said that it would be great to see a similar analysis performed in the foothills and mountains of Western North Carolina. So I don't know of any plans for that, but I imagine with the flooding we had last year out west, that could be something that emergency management or even, I know DOT lost structures. I'm sure there's interest in looking that way, and it'll probably come there.
Yes, I agree. I think there's a lot of areas around our state being affected by flooding. And like I said, the mountain counties too, they're similar to the coast where we don't have big cities out there that have all the tax base and like engineering staff that you would have, you know, that you have in like Charlotte and Winston-Salem. You know, we have that in the Piedmont, but we don't have that in these smaller communities. They don't have the same capacity.
For sure. And what do you know, Jason even said strong work. Thanks, Jason. And Tim had a question I was interested in, because I'm not a farmer, but interested in the water farming practice. And so he asked if private farms participate in Florida, and if so, what is the incentive? And it seems there would be some risk involved. So I don't know if they have extra insurance they can get or something. But.
Yes. Now, I believe they are compensated. There's a system for that. And that's what we looked at with our kind of the farmer work that was done. Again, this was led by the Soil and Water Conservation Foundation. We have Farm Bureau involved in that. And Chapel Hill did this survey, and they did lots of, kind of introducing this concept to them and to figure out what it would take to get them to enroll in a program. So you would have to have several things. First, there's going to be some kind of leasing type system. The farmers that they interviewed were the most optimal was the 30-year lease that had upfront payment. And then they actually looked at dollar value, and that was included in our price tag for water farming, what that kind of upfront payment and the annual leasing would be. Well, then they would also need to be paid after the storm. So if they are flooded, they need a payment so they don't lose that investment. And they found that actually desirable because they're losing crops to bad wet weather now. So this seemed like more of a better insurance for them, that if they lost the crop, that there would be a set amount. And so they would have money to plant their next year's crop, or their next crop coming up. So it was very encouraging that, as the Farm Bureau, Keith Larrick said, they didn't close the door. They didn't slam the door to this concept. They're like, let me hear more about it. So there are farmers that are open to this. They were also asked how many acres would they enroll now, consider enrolling now. And there was quite a few acres out of these farmers that were like, yeah. In other words, these were areas where they're already experiencing issues. So, I think that was good, but there's a number of questions, like what would it do to the soils? Like if, they want to know how many days do you have to hold the water? What would that do to the soils? And so there's a real need to do some demonstrations of this first before we just start throwing out these out there. Also, these are managed systems. It's not a passive system. The wetlands, we were designed to be more passive. Of course, embankments inspection would need to be made. But we'd have to have more water management districts. We'd have to have more technical staff, that they are making sure the designs and implementation of these are correct, that there would be annual inspections after storms to make sure everything is being maintained and operated properly. Also, that here's the big storm coming, that they're making sure these devices are being, the gates are being closed on them, so they are going to operate the way they're intended, because they have this active operational need.
Yeah, true. I guess Florida they already have water management districts in place, of course.
Right, right.
Yeah, thank you. Tim says very thorough answers. Yeah, I learned a lot just listening just now, so thank you for that. Jason asked, it's in a similar sense, and some of that answered that probably, but he asked, do the water farms have conjunctive use opportunities, and can they grow crops during the dry periods, which sounds like they can.
They are, and those gates would stay open. You wouldn't want to close the gates unless it's something like a 25 or 50-year storm. Depending on the forecast, to close the gate. Most time these systems, it's just going to operate like any given day. It's open. Their outlet points, it's open. It's flowing out. Now, we did talk about, and this was really stressed by the farmers, they would desire a system that works across all kinds of flow. In other words, if it could have a storage component to the system that would allow them during dry times to irrigate from. Right. And then from a water quality perspective, I like the idea of combining water farming with maybe a wetland component at the bottom end. So during, base flow, normal conditions or smaller rains, we're addressing the water quality from the farms to protect downstream waters. And then it would be operational in the flood type situation to give that flood mitigation benefit. And I think that would be really help with the economics of this. If we think through, we don't just design for one thing. You know, as I've stressed that, don't just do one approach. We've got to integrate, but consider water across, we're going to see more extremes. It's going to be less normal, more dry, more wet. So how can we design and bridge across those different conditions and the needs of the farmer versus the need of that downstream, whatever you're trying to protect from flooding, versus that downstream, maybe creek that's a primary nursery area for fish. So we need to be more creative and think across, more diverse with our solutions. I challenge those engineers to think about that.
Thanks, Barbara. I don't see any questions right now. So I had one that might be, who knows, you can dismiss it if you want. We looked at set events in the past, like Matthew and Hurricane Floyd. And was just curious if y'all thought about, and maybe even for a future study, of doing any storm shifting and taking those old events and just looking like, what if they traveled a little bit further inland or set at a certain spot for a longer period of time? And some of that is captured by the 100-year and 500-year analysis, but in terms of just hydrograph shape and timing of,
well, another project, not for this, not for natural infrastructure, but for another project we did in the Neuse, funded by DOT. We looked at future climate. And so we worked with the Southeast Climate Adaptation Science Center. I'm probably getting their acronym wrong. They're based out of NC State, and they did a downscaling of global climate models. They did 3 separate models, and they gave us these Hurricane Matthew in a futuristic storm, and it did exactly that. Some areas that had a lot of rain in Matthew didn't get it, and other areas have heavier rain. We looked at also the return interval storms under this future climate. So they gave us this new gridded rainfall that we put on the Neuse model. That was the AECOM model. And we found very scary projections for around 2100, where in fact that water levels in along the river, Goldsboro, Kinston, down east could be as 2 foot higher in a future Hurricane Matthew or more. That was kind of the minimum. In fact, we use the HEC-RAS model, the existing, effective model, and the water levels were coming outside the bounds of that model. So in other words, it had a floodplain, it didn't continue, it had a wall at the edge. So that's why it was showing like 5 foot. Well, that was not accurate because it was hitting a wall and the model is not extending further out. So it's kind of scary that we're going beyond what the Army Corps even considered possible for flooding on the river. So that's concerning, and that does happen. That it will shift the storms. The temperature variables will cause the storms to move differently, and we see that. We saw that with Florence, where it sat longer, dumped more rain.
Yeah, definitely.
Yeah, somebody post that Southeast Climate Adaptation Science Center. Thank you, Jean. I always get tangled up in that one.
Yeah, that's great. Well, if anyone has any other questions, please offer them. Yeah, Anna has sent the link about feedback for this program. I know y'all should have received an email with a form. We can wait just a second. And Anna, feel free to jump in if you're like, no, we have to cut this off right away.
No, thank you so much, Barbara, for presenting today. We've heard some amazing information. I know everybody got what they came for, hopefully.
Yeah.
But yeah, you guys continue to ask questions. We have no real-time limit. I believe we were scheduled till 12 today. So yeah, it's been great. And we want to, again, thank our sponsor, Res, for today. awesome to be able to continue to do opportunities. And even though I know this is a Zoom webinar, some people are question what we use that sponsorship money with in this virtual realm, but we do process the recording of these webinars and make them accessible, and they are stored on the website and sent to those who register. So yeah, that's an important step that NCWRA has really been making an effort to follow up on now that we've gone virtual for the last several years. So, PDH credits, I'll just remind you that the online survey is a requirement, and there is a paper survey, but I'm happy to answer any questions. And yeah, Jason says next forum in person. I agree. You guys don't miss the opportunity to join NCWRA at the annual conference coming up in March. And they've got some other good programming coming soon. Those will be announced for future webinars and forums in person. Matt, did you have any last comments?
No, I think that's great. I definitely want to reiterate, just thank you, Barbara, for the presentation. Thank you, Rez, for your sponsorship. This was very entertaining and just an exciting presentation to listen to. On behalf of Jason Dahl, I'll make a plug that the National AWRA Conference is coming next year, I think, in 2023. So if you want to be a part of planning that, NCWRA would be happy to have you volunteer and support Jason in that. He's doing a lot to bring that here. But other than that, I mean, we're just thankful that y'all are able to participate and join us today. Hope to see you at the conference next month.
Okay, one last call for any additional comments from the WRI team. Barbara, Rez is on, or was on. One last call. Again, thanks everybody for joining today. Enjoy your Tuesday. I believe it's Taco Tuesday and National Margarita Day. So, you know, lots of things to celebrate. You guys enjoy the rest of your days. Thank you.
Thank you.